So gas collection, yeah. Do you remember group 2 chemistry? This is also in the group 2 AS and A2, yeah. So let's think about the carbonate. The carbonate will decompose to give you MO and CO2. Agree? You know, M refers to group 2. So it's just M2 plus then CO3 2 minus, then M2 plus O2 minus. Okay, that's so far?
Yep.
All right. Now that is not very exciting, but you can still collect the gas then. How in the world are you going to collect the gas? Have you done any paper 5 on this at all? No? Never seen this before? Have you ever done this in the lab?
I haven't tried any paper 5.
Oh, okay. So usually when we want to collect the gas, so you could heat it. Well, there are many ways of collecting gas, right? But one of which is going to be using a gas syringe. Have you heard of gas syringe before?
Yeah.
So gas syringe has these lines that allow you to collect, well, they allow you to read, right? So, you know, I'm just drawing a very basic gas syringe. So this is a gas syringe. So these are what we call graduated lines, but gas syringe comes with graduated lines because they allow you to collect gas and read the volume anyway. So I'm trying to heat up a solid. So I don't heat it up in a gas syringe. Yeah? This is just a gas. I guess I could collect it like this if I have to. So I will heat up. I will heat up in a blah 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 blah. This one could be a boiling tube. Okay, and of course you need to heat. So this is my heat source or my Bunsen burner. My Bunsen burner, the blue flame will be able to do this. And this is my solid. This is my solid group 2 carbonate. And this is seal tight. This is rubber bunk. So basically, you must have an A-tight system. So A-tight system. Do you know why you must have an A-tight system here? Do you know why it's
we
A-tight?
don't want any gas to leak.
Yep, so no gas escape, and therefore it can be more accurate. And of course, as the gas is being produced, the gas is going to push onto the walls of the gas syringe, and then it's going to go that way as it fills up the gas syringe, and you can read the volume there. Does that make sense?
Yep.
Okay, now I'm going to show you another gas collection. Have you heard of downward delivery?
Oh, the one where you do it underwater?
Yep. Have you done the experiment before?
Yeah.
Okay. So will that work here? That's the question. Will it work here? Let me see. So I want to like that. And then I'll have a measuring cylinder, something like that. And then I'll have like that. And then the water like that. Yeah, have you seen that before?
Yes.
So that is downward delivery. And if I just draw that with a blue line there, so there is gas collected. And of course, we use a measuring cylinder there, which is less accurate than a gas syringe, but that is over water. Now, my question is this okay? Is this suitable for collecting CO2? First of all, can it collect CO2 or not?
I think it can.
Can. Yes, you can collect, but is it suitable or not?
No.
Why?
I think the carbon dioxide dissolves in water.
Yep, so you get carbonated drink like Coca-Cola, Sprite and stuff. So carbon dioxide can dissolve in water. So, you know, your volume is going to be lesser than what you get. All right, happy?
Yeah.
Okay, I'm going to ask you a question now. So this is MCO3 going to MO plus CO2. Okay, so let's say this experiment is to confirm the identity of M, right? And we know we are trying to get the volume of CO2, and we know the mass of the MCO3. Okay, so far, so you can get the mass of MCO3 by having empty empty container, and then the mass of solid and container. Do you know why I'm doing that? So before the experiment, you have the mass of empty container. And then you have mass of container and MCO3. So therefore, the mass of MCO3 used will be equal to 1 minus 2. Can you follow that?
Yeah.
Okay. All right. So now after that, oops, sorry. Let's say this is number 3. So this is equal to 3, let's say. Now, after you have that, you have the mass of that, but you don't know the M. So you don't know the MR. But you're collecting CO2. You're collecting CO2, right? And you know the volume of CO2 collected. Okay, so far, you know the volume of CO2 collected. So the mole of MCO3 is to the mole of CO2 is 1:1. On the right-hand side, you have the mole of that, but it is a solid. So for solid is the mass of MCO3 divided by the MR of MCO3. You can follow, yeah? And then at the bottom, I have the volume of CO2, and this is all done at room temperature and pressure. So we know the molar volume of a gas is 24 dm³ per mole. 1 mole of any gas occupies this volume at room temperature and pressure. And this thing don't record the dm³, and this thing, the small one that we use in the lab, don't record the dm³. Typically, they record to cm³, right? So I'm going to use 24,000 because this is in cm³. So this is in cm³ per mole. Are you with me so far? Okay, because I specify this is in cm³, yeah? Now, how are you going to find the identity of M? Well, we need the MR. So I'm going to make that the subject. Oh gosh, okay, I hope you can see the map, yeah? So it's going to be MCO3 multiplied by 24,000 divided by the volume of CO2 in cm³. Can you see that?
Yeah.
Are you sure? You can see that, yeah? Okay. Now, after I get that, my question is, this method versus this method. Based on what you said, the CO2 can dissolve in water, right? The CO2 can dissolve in water. How is this going to affect the value of MCO3 molecular mass? Is it going to be higher or lower?
Well, it should be higher.
Explain yourself. Explain yourself.
Because if carbon dioxide gets dissolved inside water, the collected volume of carbon dioxide will be smaller. Therefore, because the mass, the MR of MCO3 is inversely proportional to the volume of the carbon dioxide, therefore it will increase as the volume of carbon dioxide decreases.
Okay, so the MR or MCO3 calculated will be, sorry, did you say smaller or bigger?
Bigger.
Okay. Okay, so because that is bigger and those things are fixed, then you can take away 12, you can take away 16 times 3, then your AR of M is going to be bigger. Okay, so this is about error analysis. In paper 5, I'm not saying this exact question will come up, but it's all about, is it bigger, is it smaller, and why? So you need to try and rationalize yourself. And the best way to think about it is go back to your data. What did you investigate? And this is one thing that can happen. How does the effect, how does something else that is done in the questions, how does that affect any of these variables, and whether they will change the final result or not, something like that. Okay, are you all right so far? Now there's another one, which is MnO3 twice. What does that produce when you heat it? So this is a group 2 nitrate. In A2, they like to ask you the essay, right? Group 2 nitrate thermal stability.
Yep.
Yep. What does that give you?
NO2 and oxygen.
Yeah. Okay. Come on. Balance my equation for me.
And MO.
Is that equation balance?
No, yeah.
Is that it? Is that balance?
No, we have to
balance. Of course not. Okay.
No,
Can you balance it?
2 NO2. And 4, 6, half O2.
Okay, so this is a gas, and this is a gas, and this is a solid, and solid. How do you know this reaction happened? What is the indication that this reaction happens? What do you see?
We see NO2 is a
Sorry, excuse me. Sorry, you were saying NO2 is?
a colored gas.
It is, and you should know that it's a brown gas. Yeah, this is a common observation, and they really like to ask you as well. So you know, sometimes you can have MgNO3 twice dot 6H2O, and this one when you heat it, they're gonna give you MgO solid, gonna give you 2 NO2 gas, half O2 gas, and then they're gonna give you 6H2O as well. Okay, so this is a solid, this is a gas, and this is a gas. This is a gas when it's heated, but this actually happened in 2 stages. Did you know that it happened in 2 stages? The first thing that will happen is you will get the nitrate, and then the 6H2O will come off as a gas because it's very, very hot. Okay, so there's still solid, there's solid. And then the second stage is when the whole thing will happen, when you will decompose and give you the oxide, the NO2, as well as the 6H2O there. Okay, now can you tell me what do you see in the first step? Observation, right? So this is a hydrated solid. As you know, hydrated solid means it has water of crystallization. Water of crystallization is from your IGCSE stuff. So you can tell me, what will you see in this first reaction here? Have you ever done this in paper 3? Have you ever heated a hydrated solid in paper 3?
No.
So when you heat the solid is there. So it has got water crystallization, right? So the first thing that will come off will be your water of crystallization. It's very, very hot. So, you know, the H2O is going to go into gas, and then it will go up the tube. This part of the tube is cold. So the H2O gas is going to cool down and condense on the upper part of the tube. So what you see is, you see colorless liquid. This is your observation, yeah? You cannot say it's water because you cannot see water, you see. You can only see liquid, and you see the color, so it's colorless liquid on the upper part of the tube. Have you ever seen that before?
Yeah.
I don't know, but you say you haven't seen it before, so you know. And then the second bit is, now that all the water crystallization is gone, and you heat harder, you heat stronger, what's going to happen is you're going to get something. You're going to get NO2 gas, and you're going to get O2 gas. But you cannot see O2 gas, but you can see NO2 gas, and that is the second observation. You see a brown gas. Does that make sense?
Yeah.
What will you see
Dr.
at the end of...
Will the NO2 gas sink?
Sorry, will the NO2 gas what?
Sink.
Sink. You mean S-I-N-K, is it?
Yeah.
It would, but it would probably also diffuse. As you know, gas molecules will travel in all directions randomly, yeah? Right? From a region of high concentration to a region of low concentration. So, you know, it might sink, but it will also diffuse in all directions, you know, from where you have a lot of it, and it will escape it until you don't see the brown thing eventually, because it will diffuse. All right. I am just saying that, you know, it will escape. I'm not saying that it will definitely go up. I'm just saying that it will escape. Okay. But you will see a brown gas. Okay. Sometimes people could also mention that you get a white solid left behind. So you get a white solid left behind. It is definitely not a colored solid because, you know, doesn't contain any transition metal at all. As for this oxygen gas, you cannot see it. You can only test for it. You can test with glowing split, and you will get it relighting. Now, my question really is, can we collect the volume of NO2 and O2? There's something that we need to investigate. Okay, so let's say we have MgNO3 twice, give me an MgO and 2NO2 and half O2. Okay, so now my question is, how are you going to collect this? How are you going to collect this and this separately? So we know about gas collection. We have no problem at all. We know that we can heat, right? Should be no problem heating. So I can heat up in a tube like this. So this is a slightly different setup. There are many, many different setups. This is just one of the many. Do I want to collect the gas straight away into gas storage? Do I want this? Is this
No,
good? Why not?
because we're heating the boiling tube, which is going to make the air hot. So the pressure would be different inside the gas range.
Okay, but then this is how we can collect gas, right? Actually, it will work with magnesium carbonate. Why shouldn't it work here? It's not based on what you say, although what you say is perfectly logical. There's a bit of air left inside, and that could affect the reading. So, you know, what you record there might not be 100% the volume of the gases, because there could be the volume of the air that's expanding and, you know, filling up the space. But what I'm trying to say is this is not a suitable apparatus, because your objective is collect them separately. Can you separate this gas? So this question is not just about gas collection, it's about separation. Can you separate these two gas? That's the question actually. Okay. Yes, they're asking you on gas collection, but can you collect them separately? It means you need to separate the gas. So by collecting in just one gas syringe, they're gonna mix. So not good, because you are not achieving your objective. Okay. So which one would you want to collect first? First of all, you need to think, how are you going to separate them? What kind of different properties do they have?
They might have different boiling temperatures.
Boiling point. Okay, we are collecting the gas, which is already a gas. Yeah. So, you know, if you want to condense them, they are not like water. If you have H2O gas, this is easy to condense. Do you know why? Because you just need ice and you can condense it. Do you think it's easy to condense this in the lab, in the school laboratory? It's not easy. The boiling point is like minus 100 something. It's very difficult. You don't just go and use the ice bath, right? It's going to be quite tricky. Think of, okay, I'm not saying it's impossible. Yes, it is possible if you know their boiling point, but you need more than just ice. You probably need liquid nitrogen. I don't know their boiling point. That is not the first thing I would think in my mind, actually. I would be tempted to think about acidic oxide, and this is neutral. There's something I'll be tempted to think about. Do you agree?
Yeah.
So if I want to know the mass of NO2 present, the mass of O2 present, or the volume of O2, I would probably, this is like your AS combustion analysis. They like to ask you the carbon dioxide, right? The carbon dioxide is absorbed by soda lime, absorbed by sodium hydroxide or potassium hydroxide. Do you remember doing that vaguely in AS? Topic 1, calculation?
I don't remember anything.
You don't remember? Okay, this could very well be a paper 5 question as well. Yeah? They'll ask you how do you remove the CO2? Well, you can absorb it, but of course you need the mass. You need the mass of the sodium hydroxide to begin with. Then the gas is going to be reacting with the solid. All right. So I'm not saying this is the only way to do it. Yeah. Okay. There are many ways to do paper 5. I'm just saying that this is something that I can imagine that will happen. All right. So something goes in, and then something comes out again. So if I want this thing to go in, okay, I am not saying that my way is the only thing that is possible. No, yeah, I'm saying that this is just one of the many possibility. So there's your solid and then OH. This will absorb the acidic NO2 gas. And then, which means I can then collect on the gas syringe. My diagram is getting worse and worse. But anyway, I hope you get my drift. My drift is that this one here will be O2 collected. Now the question is, how in the world do I need, well, how in the world am I going to get the mass of NO2 absorbed? How much NO2, what sort of reading do I need?
You need the volume of O2 collected, and then you will need the MR of NO2.
Okay. But experimentally speaking, how can I get the mass of NO2 absorbed? So this is a solid, right? This is not a solution, right? So the gas that comes in, the acidic gas is going to react with this, and it's still going to form a solid. Do you agree? So NO2 is nitrogen plus 4, oxidation number. When they react with NaOH, suggest what you will get. Acid-base reaction, isn't it? What will you get? Writing equation. So this is acidic oxide. And then you have base or you have alkali. What are you going to do here? What do you get? Neutralization. What are the product of neutralization?
NOH4.
Nope. You're going to get a salt and then you're going to get water. Do you agree? Salt and water. Have you learned neutralization before? Acid plus base give you salt and water.
Yeah.
Okay. They are going to give you. Are you sure? Okay. So I think the salt. Okay, the salt is going to be a bit tricky because I want to do acid base. I don't want to do redox. That's the problem, you see. You might have a point here. Because this is nitrogen plus 4, when I have NO2 minus, NO3 minus, this is nitrogen plus 3, this is nitrogen plus 5. I don't know about this, but it's definitely a salt. It's going to be a salt. That's all I can tell you. I really don't know about. Because if I change the oxidation number, it is going to be a redox. But we know neutralization is not redox. But hey, what we know is there will be neutralization. And if we know the mass of NaOH solid, before reactions, okay, and we know the mass of solid product after the reactions. So the difference is going to be the mass of the NO2. Agree? Okay, so this is what you measure. Those two are what you measure. But of course, the solid are inside the tube, so you know it's plus the container. So we are going to weigh it together with the container. This is more in planning question. What do you need to measure? You need this and this, then you can calculate this. And then we can get the volume of O2 from the gas syringe. There's no problem. Mass of MR, like you said, would tell us the mole of NO2. Volume divided by molar volume would tell us the mole of O2. And if we don't know the identity of the metal, if this is M, just a group 2 metal, just a group 2 oxide, we can, from this information, we can get the identity of the metal. Do you agree? Just like how we did in the previous question, we can do things like this and get the identity of the metal nitrate that we try to decompose, and therefore we can get the identity of the metal. Happy? Not happy? Not sure what I've just talked about?
I am.